In this video, we are going to go over the paper titled ProbTS, a Unified Toolkit to Probe Deep Time Series Forecasting. This paper from Microsoft has been published on arXiv in October 11, 2023 and is relatively new. I mean, it's very new at the time I'm recording this video. And we are going to go over it, which is going to introduce a package called ProbTS, based on the title of the article as well, that has to do with time series predictions for short-term and long-term forecastings. It's going to be something similar to Nixla, to GlowonTS, and this package is going to provide the opportunity to test and evaluate different models that have been developed for different purposes and different applications, and try to kind of see what exactly are the things that empirically can be asserted as the causes for their good or bad performance in different scenarios. So let's start with its abstract. Now, all of you know that there have been a lot of developments in the deep learning domain. Specifically for the time series forecasting also, there have been many developments, and they can mainly be categorized into two branches. One focusing on crafting specific neural architectures that are designed for time series, namely those that have the inductive bias towards the time series. And two, harnessing advanced deep generative models for probabilistic forecasting. So basically these are the kind of two things. Now, there are different data scenarios, different methodological focuses, different decoding schemes, for example, autoregressive versus non-autoregressive, and many other things, which the purpose of this software, this ProbTS package, which is going to be publicly available, and this article in general, is to kind of allow a toolkit to synergize and compare these different branches, these different methodologies, these different decoding schemes, and see what works where. And that is going to hopefully lead to some extent revolutionizing the time series domain in order for us to understand when is a particular methodology good to use. Now, here are the main characteristics of ProbTS, which is unified data module, a modularized model module, a comprehensive evaluator module. Now, the package at the time of this video is not publicly available, or at least I haven't found it, but as you can see, it's not just going to be something that is released, but it's going to be a framework that is going to make development easier. So it's basically provides this abstraction, the unified data module, the model module, the evaluator module, and this is going to allow the developers hopefully to build their own models as well and enable basically the easy evaluation of these different models and methodologies once they are integrated into this format. All in all, pretty interesting so far. So let's continue. The introduction starts with discussing some of the applications of time series forecasting. You can see a lot of applications such as climate projections, sustainable systems, etc. The introduction also discusses some examples of strong trending and seasonality patterns as characteristics of the time series that are important. Now, we will go over these, but seasonality patterns have to do with these kinds of periodic expected changes, and strong trends, meaning that, for example, you could see something like a time series that if you take and smoothen it over a long period of time, you could see this kind of like upward trend or downward trend. So there is going to be this additional thing added to the time series. So that would be characterizing a strong trend, for example. And the paper, throughout the paper, you will see that trends and seasonalities are two perhaps most important characteristics of the time series that would dictate, aside from the fact that whether or not you're looking at a short-term or long-term horizon, what kind of algorithm works best. Here you can see the different data characteristics are pointed out. For example, basically you have forecasting horizons that also matter, and basically all of these things. So the question that ProbTS is trying to answer is this: how would the methodologies from one branch perform in scenarios traditionally addressed by the other branch? The first interesting research question is, can we integrate the strengths of both branches to revolutionize time series forecasting? In other words, can we identify the components in each methodology that makes it uniquely good for that particular scenario for which it was designed, and then provide something combinational that takes, let's say, the best parts of each different branches that creates this kind of composite, let's say, solution for us that works best for a particular scenario that has not been let's say, investigated under that particular solution that we are hoping to kind of know more about. The other question has to do with the decoding scheme. When is autoregressive decoding better than the non-autoregressive decoding. As for the motivation, they state that no solution currently bridges the chasm between these branches, especially given the vast divergences in data scenarios, methodological focuses, and decoding schemes. So you can see that you have these three main axes of change, these degrees of freedom, and a methodology or a software library that is enabling you to do all of those things and test all of these things in different data scenarios prior to ProbTS either didn't exist or did not exist in this format up to their knowledge. So you can see again that ProbTS is going to offer data module, model module, and evaluator module. And again, the goal would be to bridge these two distinct research branches in time series forecasting and provide in-depth analysis and comprehensive evaluation of leading methodologies. Going over the contributions of this paper again, some of their findings are that the long-term forecasting scenarios predominantly exhibit more significant trending and more significant seasonality. So the seasonality and trending, as expected, is going to be manifested more extremely in the long-term horizons. Now, that's one thing that they have. Now, the latter, meaning the short-term forecasting, is going to display more complicated data distribution. So that kind of remaining component of the time series signal is going to be more complex and exhibiting more complex patterns in the short-term horizons. Of course, there are variations between the data sets and tasks, but this is kind of like a general average finding. And these differences in data characteristics, they find that greatly influence the method design. So that is another thing that we need to look for, not just what model is going to be state of the art, but what kind of characteristics does the data in this particular time series dataset have that renders a particular model good for it. Then they have continued to identify pros and cons of different methodological focuses. Now, one thing that they consider is the probabilistic forecasting methods, and they show that it's better for modeling complex data distributions. However, they may produce poor point forecasts. So they have superior CRPS score, but perhaps a inferior NMAE score. So that kind of thing has to also be taken into consideration, and what kind of, let's say, measurement is going to be more important can in some cases be determined by the task itself. Now, they find that customized network architectures, those that have inductive bias for time series, specifically addressing the challenges induced by trending and seasonality, perform remarkably well in the long-term forecasting. So that's another thing that they have. And they look at the underexplored domain of effective network architectures for short-term forecasting and basically provide incentive for future research in this domain as well. Then going for the decoding schemes, they find that looking at the autoregressive scheme, it's going to excel when there are strong seasonality. But when there's trending, autoregressive is going to struggle a bit. Okay. And this is again for long-term forecasting. So again, they find, and we will go over it, that in the long-term forecasting where where seasonality and trends are manifested more extremely, autoregressive schemes basically work well when there is a strong seasonality, indicating that autoregressive decoding is capable of understanding that seasonality, but it struggles with the pronounced trending. So when there is a trending pattern in the data, autoregressive decoding might not be optimal. Again, all of these are for the long-term horizons. Now, for the short-term horizons, they will show that it kind of performs equally well for the short-term forecasting. In the related works, they discussed that significant advancements in the time series domain gave rise to two distinct research branches: effective network architecture designed for time series, and the other for advancing probabilistic estimations such as diffusion models and things as such. In branch number 1, namely the neural architecture designed for time series forecasting, they group it into multilayer perceptrons, these works, and customized RNNs or CNNs, which are these works, and more recently transformer-based variants such as these works here. They discussed non-autoregressive decoding as a characterization of basically these approaches, mostly. And they mentioned that recent transformer variants especially primarily focus on long-term forecasting scenarios that have prominent trending and high seasonality patterns, and that often they are limited to point forecasts. In branch number 2, they go over probabilistic estimations in time series forecasting, commonly referred to as deep probabilistic time series forecasting. And the idea is to this time capture the complex data distributions rather than those kinds of point predictions. They have examples such as predefined likelihood functions, Gaussian copulas, and more recent methodologies harnessing deep generative models. They mentioned that they primarily have to do with short-term forecasting scenarios, often overlooking the challenges posed by long-term data characteristics that have to do with trending and seasonality manifested in the more extreme, and that these kinds of methodologies employ both autoregressive and non-autoregressive decoders. So, decoding scheme in the previous methodologies for the neural architecture design have often been non-autoregressive, but in this case, autoregressive also shows itself. In terms of toolkits that are currently available, there have been some toolkits made available. One is those that primarily are focused on point forecasting, such as Profit, such as scikit-learn time, TSAI from FastAI, TSLib, and so on. For the probabilistic forecasting, there is GluonTS, there is PyTorch-TS, and so on. As for this kind of unifying these two objectives in these two domains, PyTorch forecasting and neural forecast are two packages that try to do that, but they have a limited range of approaches apparently. All in all, ProbTS is here to solve this kind of gap in the research. Consider the time series signal. You have x of t and k. T is going to be the index for the time series, and k is going to be the index over the dimension of the features, for example. So in other words, t is going to be time, k is going to be variant, and these are indices. Now, if you take the xt vector, it's going to be a k-dimensional vector associated with basically the k variance in the x, and each one of those variants is xtk. This is going to be, let's say, one slice of this time series is sliced over the dimension of time. There are also covariant vectors, ctk, that are basically the covariates associated with the kth dimension. Now, in one case, you have xt minus l until t and ct minus l until t. So on the source part, you have these two observed. And the goal is to predict xt plus 1 to t plus t. In the non-autoregressive scheme, you also have t plus t for the covariates. But yeah, look at this. You're going to have an encoder and a forecaster. Encoder is supposed to take that input and map it to a d-dimensional edge. For example, in the case of autoregressive, you have this encoder parameterized by phi parameter set. Take x, the vector at the previous time step, the covariate at this time step, and the output at the previous time step. It'll take these three as its input in order to capture all of that historical information as well, and using that is going to generate the HT. So this is the autoregressive decoding. The non-autoregressive decoding is going to, in one shot, create HT plus 1 all the way until t plus t using the covariates t minus l to t plus t, so all of it for source and target, and t minus l to t input. So it'll take these two and it'll, in one shot, create this. Now, in the case of the point forecasting, you have this forecaster parameterized by theta, and it will basically parameterize the approximation of the point value. So using this HT, it's going to give you that estimation for a particular timestamp. Now, in the case of probabilistic forecasting, this theta given HT is going to parameterize this distribution for xt, and then you're going to sample the estimated point value from this distribution. Alright, let's go over the main components of ProbTS again. So you have the data module. So the data module, you have model module, evaluator, and then some discussions on the implementation. So the data module is going to unify varied data scenarios. Okay, so the goal is to make evaluation and implementation more easier and streamlined in order to provide a fair and easy to use comparison. Then they have quantitative approaches to visually delineate data sets and intrinsic characteristics of them. In particular, they have trends and seasonalities separated using things such as STL decomposition in the time series, and then they evaluate the similarity between data distributions to a Gaussian, and there are different metrics and measurements that we will discuss in the results. As for the model, it's going to be a modularized model module in this package, and you're going to have neural network architectures, you have forecasting paradigms, and you have decoding schemes. So the construction of the models is going to be enabled by having this encoder and forecaster blocks in some sense, and those are going to be used. As for the evaluator, they have different methodologies and measurements implemented. You have the mean absolute error, normalized mean absolute error, They have mean squared error and continuous ranked probability score. They have tried to be careful with the implementation. They conducted extensive grid search to identify the most effective setups and so on. Let's take a look at this building block. So this is the ProbTS package. The data is going to have data sets. You have different forecasting horizons that signifies them, so short-term versus long-term. You have intrinsic characteristics associated with this data set. So for example, trend and seasonality can be kind of decomposed using methodologies such as the paper that was proposed in 1976. Distribution can be assessed by considering the Jensen-Shannon divergence and things as such, and compare it against, for example, Gaussian and things like that. So there are these different characteristics that could be, aside from just visually seeing them, could be quantified to a certain extent. Then you have preprocessings, normalizations, splitting, feature embedding, adding sequence lags, and so on, which definitely would provide you with a lot of options for hyperparameters that they have tried to optimize over in order to kind of remove these variants as the confounding factor. So you have the autoregressive and non-autoregressive decoding schemes. So you can, again, let's go a little bit closer and to take a look. And sorry about this additional line. So as you can see for the autoregressive decoding, if you look at this particular part where HT is being generated, in generating HT using this encoder F5, you're taking the covariate vector at time step t, you're taking the output at step t minus 1 of the previous step, and you're taking these two, and you're also taking this xt, and this is kind of a non-teacher forcing setting. So you have this x hat t, you're feeding this one as well, and then basically, in the case of ht, you're feeding xt minus 1 hat, and then so with this, and with this, the encoder in the autoregressive setup generates ht. Now in the non-autoregressive setup, you have xt minus l to t, so let's say you have this component, and you also have the covariates for the target objective, because you could just want to have the output in one setup, so there's no opportunity to use them later in some sense. So you take that, and you take this, and the encoder is going to take this and in one shot generate ht plus 1 to t plus t, or the t components in the output. So with that, the predictor is going to take that and predict x hat t plus 1 to t plus t. And then going back away from here, so you have different encoders, you have RNNs, transformers, you have customized time series models, you have TimesNet, patch, TST, D-linear, and such. For the forecasters, you have the probabilistic and point forecasting, such as, for example, you have diffusion models, you have linear mappings and such. And these would be basically the modeling components. So you can see that everything's pretty much modular. And then going to the evaluator, you have different characteristics, different measures. You have MSE, MAE, CRPS, CRPS sum, and so on. Note that you might know that CRPS could be kind of like a pointer distribution generalizations of MAE, and that's one of the prominent measures used in this paper as well. So chapter 4 or section 4 is ProbDeep's time series forecasting, and they go over these different axes of characterization of different methodologies. And I say methodologies, not models, because they are also characterized by things beyond the model, such as the decoding scheme. So they first go over the variations in data scenarios, and they want to evaluate the strengths and weaknesses of different methodological focuses and decoding schemes. And then they are going to compare the computational efficiencies of these approaches later on. So let's go over these. Let's go over their baseline selection. Now, for the probabilistic approaches, they have those that focus on advanced density estimation techniques such as normalized flows, these methodologies, and diffusion models, namely TimeGrad and CSDI. They also consider different neural network architectures such as linear, GRU, transformers, coupled with a linear forecaster without probabilistic estimation. They have global mean and batch mean as baselines to assess forecasting difficulty, and they also include TimeNet and patch TSD as models with inductive bias for time series, and also NHITS and LTSF linear, which are again good for time series data. I encourage you to go over the details of these methodologies and read more about each one of them from their own papers. Now in table 3, this one, they go over some of these datasets. So you have this datasets, you have trend and seasonality and the Jensen-Shannon divergence from Gaussian. and you can see the different characteristics shown here. So you have exchange, solar, electricity, you have the long term, so L and S are short term and long term, and you can see that going from the short term to long term, you can see that the magnitude of trend, sort of this trend power that is defined in the appendix, and we will go over it later on, is increased compared to the short term. You can see that there are datasets such as Wikipedia S, where if you take a look at them, the Janssen-Shannon divergence between them and the Gaussian indicates that they are close, so they don't require super complicated modeling capabilities perhaps for these datasets, and their tasks to be done efficiently. And for example, you have datasets such as Solar S, you can see a larger Janssen-Shannon divergence, and that would technically necessitate possibly more advanced distribution modeling designs to be needed. Note that table 2 also signifies the summary of these datasets. So you have long-term and short-term datasets. From each you have these different categories. You can see the number of variants, you can see the range, you can see the frequency, the time steps in each one of them, and the description. So you have electricity, transformer, temperature per hour, and these datasets, and you have these datasets for the short-term horizons. Noting that the length of the horizons is actually an important component in assessing these evaluations, we will go over the point versus probabilistic estimation. So you have two categories here. So, sorry, not categories, two kind of prominent results here. The first one is that probabilistic methods excel in modeling complex data distributions. So here, the focus is more on short-term ones, for which the probabilistic methods is good. So you have time grads and CSDI as the example of these. You can see that they demonstrate superior performance in NMAE and CRPS metrics for the short-term forecasting, again, more notable in these datasets. One other thing is that in the case of the long-term forecast, they mentioned that they cannot compare probabilistic and point estimations because of the complication that comes with, the multifaceted nature of this and the fact that you have to deal with a longer horizon. The other component is probabilistic methods may produce forecasts that are poorer in terms of the point estimation and point values, but superior CRPS scores. So you can see that, for example, CSDI, and we will go over the table in the next slide, that you have a better CRPS score but worse NMAE score, reflecting precise distribution approximation but weaker point forecasts. So they mentioned that this discrepancy is indicative of inherent limitations in current probabilistic models, shedding light on the prevailing preferences for CRPS in evaluation. So CRPS is is highly preferred, and at the same time you have to understand that NMAE might be inferior in the probabilistic methods. Next, we go over the customized models with inductive bias for the time series, and you have the general neural architectures to be used for the time series prediction task. Now, the question here is whether a customized neural architecture is actually necessary. So whether time series inductive bias is essential or not. So the first kind of result here is customized network architectures or network architectures with time series inductive bias perform remarkably well on long-term forecasting. So they mentioned that for long-term forecasting, it does appear that this kind of inductive bias actually helps. So you have dlinear and PagerDuty significantly outperforming models that employ probabilistic estimation techniques that rely solely on general architectures. So that's one thing. Now, they mentioned that given that data exhibits more pronounced seasonality and trends in longer forecasting horizons, then this superiority of the models with time series inductive bias can be associated with the trends and seasonality. So the fact that the longer term horizons are often associated with a higher degree of seasonality and trends, that basically could be the cause why this kind of inductive bias would be helpful. Now, for the shorter term forecasting, the customized network architecture remains underexplored. At least in the results, it doesn't show that this kind of architecture would result in significant benefits, but this is still an area that has to be investigated. Which brings us to one of the main points of ProbTS, which can we use kind of a combination of the power that comes with the inductive bias of the time series and the probabilistic estimation methodology to create a solution that actually has the best of both worlds. You can see the table of results here. You have mean and standard deviation on short-term forecasting data sets. So you have the short-term forecasting data sets. You have the global mean and batch mean as one of the baselines here. You have linear GRU transformers. You have these probabilistic methods right here, and you have these methods right here. And you have the data sets on these axes. And you can see these probabilistic models work very efficiently in this kind of short-term data sets. Now, going towards the longer-term data, you can see some of the examples here. For example, you have data such as these. You can see that NMAE is not great on the CSDI, but CRPS seems to be the best, and so on and so forth. Next, they talk about the decoding scheme, autoregressive versus non-autoregressive, because it's one of the important factors in here. Now, one thing that they find out, and I mentioned, is autoregressive models excel with strong seasonality, but struggle with the pronounced trends. So considering the trends and seasonality being two factors that are also more pronounced when it comes to the longer term horizons, this autoregressive decoding schemes seems to be one of those design decisions which favors a case where there is a strong seasonality, but there is not a pronounced trend in the data. However, they mentioned that exceptions also exist. For example, in the traffic data set, which has minimal trend strength, yeah. All in all, empirically, they conjecture that autoregressive decoding might not be the optimal choice for the cases where you have longer-term pronounced trends. And then the second part is that both decoding schemes, namely autoregressive and non-autoregressive, for the short-term forecasting seem to be kind of doing the equal job, or equally good of a job. So they discussed that there is the limited impact of error propagation on the autoregressive methods when there is a short-term scenario is probably the cause why they kind of both do the same thing and how they are kind of relatively the same. So that's the first part. The second part that they discuss is if you have high trending, again, it might be optimal not to use the autoregressive decoding. So this paragraph kind of results from this one. Again, autoregressive methods are proficient in modeling seasonality, but apparently the representation power might not be optimal for representing longer term trends. Next, they discuss computational efficiency, and the main result is modeling high dimensional probabilistic distributions demands substantial memory and is time intensive. So again, the thing they find out is that optimization especially is crucial for cases where you're dealing with probabilistic models, such as diffusion models and things as such. And those would require additional computation power, which might not be, an optimal of a choice given the data set, given the size, given the task, and so on. Now, in conclusion, this was ProbTS package, which provided a lot of functionalities for basically evaluating different methodologies, again, including modeling, including the understanding of the characteristics of the data and the underlying task, as well as different metrics for evaluating it under different circumstances. Next, in the appendix, they talk about trends and seasonality. Now, if you have YT for a time series of yours, you can have basically that being decomposed as 3 time series, one being representation of the trend, the other one with seasonality, and the other one with the remainder of whatever it is. You can read this page, which is from basically a package that provides a methodology that was proposed somewhere, I believe, in 1976 or so, that has to do with this decomposition and how that can be done. So they followed this STL decomposition in order to break down this time series into trend, seasonality, and remainders. Once that is done, they can take the time series R, T, and RT, and you can define these two things such as the trend strength and the seasonal intensity. So that basically kind of boils down to the fact that consider the remainder basically component, and let's say it has a lower variations, however the trend exhibits a high variation. So for example, you can see a time series such as this, where this would be the trend and for example this would be the R. So the variance for this would be 0. In that case, this would be 1, and the trend strength would be 1, as you can see in some sense. One thing that is crucial in here is that you are looking at the variance of this particular time series. So if you look at here, you have this time series being adjusted for seasonality in some sense, and in this one you have adjusted for trend strength. So in some sense, when you're looking at the strength, there is no trend. When you're looking at trend, there is no strength. Both of them are compared against the remainder component. But again, you can see that 0 indicates minimal seasonality, and 1 would indicate higher seasonality. Because, for example, if seasonality, for example, is 0, all 0, or something that does not add to the variance, meaning constant in some sense. So you could take these two would be the same, they would be 1, and the result would be 0. So again, these two are just two measures of how intense the trending and seasonality are as characteristics of this data set. As for the data distribution, in order to kind of use it as a quantified value, as a quantitative estimation of to what extent you need to provide computational power for, let's say, not computational power, but representation capacity for the models in order to handle the complex patterns of the data, they provide this methodology, which means you take Gaussian distribution and you take the Jensen-Shannon divergence and you assess the similarity between each dataset distribution and the Gaussian distribution. And then you would take this over windows, and then you would just evaluate essentially the average of them. So you choose a window size of 30 for the short-term horizons, 336 for longer-term ones, and the results are summarized here. Next, they deal with the outliers. So outliers, they have global outliers and local perspective. The global view is going to take the entire data set as a Gaussian distribution and use the z-score normalization. The local perspective, again, has to rely on a window. So again, you have a 30 and 336. So this result is shown in table 7. And of course, it's another measure that you could consider in, a characteristic that could differentiate between different data sets. So you can see these values here. You have local outlier measure, global outlier measure, and so on. And there are a lot of visualization tools here that you can see. For example, time series selected from the longer term forecasting data sets. And next, going to the evaluation metrics, it's kind of straightforward. You have the mean absolute error, you have this. So again, you have K variance and T time steps. So you could consider this kind of like distance between them. Then you have the MAE sum. In the case of MAE sum, you are looking at the sum of the variance. So you have sum of the variance. So basically you're reducing over the dimension of the variance and then considering the MAE of that against the MAE of the prediction. For the case of normalized mean absolute error, you are normalizing that based on the XIT. And again, in the case of XT sum, you normalize them against the XT sum. Again, L1 norm, or the absolute value of that. Similarly, you have the mean squared error as a measurement. And the case of normalized root mean squared error. So normalized root mean squared error can have different denominators, but in this case, they are working with this particular thing here, which could be considered the L1 norm. And on the top, you have this value. And similarly, they have this sum version of it as well. And then finally, they have the CRPS, or Continuous Ranked Probability Score, which is a measure of agreement between the cumulative distribution and a observation X like this. Now, CRPS can also be shown to be kind of a generalization of the mean absolute error. So it would be something like if you take two random variables X, so it would be something like this if I'm not mistaken. So let's say this is X1. So it would be something like this as well, I think. But yeah, so the point is that it's going to be kind of a generalization of that. And the CRPS score is something that is important in this package. As for the implementation, it's implemented in PyTorch Lightning with PyTorch backend. So you have 100 batches per epoch trained for maximum of 50 epochs. And they have V100 GPUs, again, single V100 GPU, CUDA 11.3, Atom Optimizer is used, and they sample 100 times to report the metrics on the test set. For the hyperparameters, they also do grid search and things like that. Additionally, they go over model efficiency as well and provide some insights on that. In this figure, you have the point forecasts from the patch TSD methodology against the ground truth. You have some more graphics here demonstrating the forecasting intervals from time-grad model, comparisons of the computational efficiency, and so on. In here, you have the computational memory, the number of parameters in megabyte, maximum GPU memory on these different methodologies, different data sets. You have the comparison of the inference time here. And that's about it. Thank you for watching.